Today we're going to look at applied optimization problems, and we'll start with the following relatively simple problem. A farmer plans to fence in a rectangular plot to grow cabbage. Three sides of the plot will be bounded by fence and the fourth side by the wall of a long barn. The farmer has 40 feet of fence and wants to construct the plot so it has maximum area possible. What are the dimensions of that plot? And here's a picture of what's going on. Here's our long barn. Here's the plot. These three sides that are red are fence. The length of the fence on the side parallel to the barn is X, and these other two sides are Y. And what we're now going to do is look to maximize the area of that plot. And that's what we call the objective function in these problems. It's the thing we're trying to maximize or minimize. And the area of this thing is just X times Y. Now, in this particular problem, X and Y are not independent. We have 40 feet of fence. And that's reflected in what is called the constraint. The amount of fence, which is X plus 2Y, here and here, has to be 40. At this point, we want to use the constraint to change our objective function to a function of one variable, because the only sorts of functions we know how to maximize or minimize are functions of one variable. So we solve this for one of the variables. X is 40 minus 2y. We could have solved for y as well. And now we take this information and we put it back into the objective function. And you'll see that the x has been replaced by 40 minus 2y, which I've multiplied out to get 40y minus 2y squared. Now the next thing you want to do is look to see what values of y make sense in the problem, because you don't want to end up finding a point that has no physical significance. In this case, the values that make sense are 0, less than or equal to y, less than or equal to 20. Y equals 0 is a very silly plot. It's 40 feet of fence right along that wall, but you could build it. The other constraint is that x can't be negative, and that would end up being the case if y were bigger than 20. When y equals 20, this is this silly run out 20 feet, run back 20 feet, plot of size 0. Nonetheless, it's possible. Now what's nice about this is we now have a differentiable function of a single variable on a closed interval. And we know how to maximize and minimize those. You look first for critical points, and the derivative of 40y minus 2y squared is 40 minus 4y. We set that equal to 0, get 40 equals 4y, or 10 equals y, and that's our unique critical point. Our endpoints are 0 and 20, so we're just going to check our function a at those points. When y is 10, we get 400 minus 200, which is 200. When y is 0, we get 0 minus 0 is 0. And when y is 20, we get 800 minus 800 is 0. So very clearly, a equals 200 is the maximum value for the area on that interval, and it happens when y is 10. And now what we do is, since y is 10, x was 40 minus 2y, so that's 40 minus 20, or 20, and the area is 200, so the dimensions of our plot are 20 by 10. This problem was fairly easy to do for a variety of reasons, and one of them was this was a continuous function on a closed interval, and we know how to maximize and minimize such functions. Sometimes, however, our interval is not closed. But in such situations, if we have a unique critical point, we're still not in bad shape. Suppose on an interval, f of x is continuous, has a unique critical point at x equals c on that interval, and is differentiable, except possibly at the critical point. This allows for critical points where the derivative doesn't exist. But otherwise, we've got a differentiable function. Let's look at what could happen if we had just a single critical point. Okay, if it was a local maximum, this is what the first derivative test would have to look like for it. And you'll notice goes up, goes down, local max. But look, this is the whole interval. There cannot be anything else that's the global max. This has got to be it, because we go down this way and we go down that way. So the local max is a global max. And if you look at a minimum, what you're going to see is exactly the same thing. This is what the first derivative test is going to tell us. We go down, then we go up. There's no other point on the interval that can be as low as this, because we move up away and we move up away that way. So this thing is the global minimum for this interval. And what that means is, if you have a unique critical point on your interval, if you're at a local maximum, it's the global maximum. And if you're at a local minimum, it's the global minimum. Which means that our local tests, which are the first derivative test and the second derivative test, will not only tell us that we have a local minimum or maximum, they will tell us that we have a global minimum or maximum. Now we're going to look at a somewhat more complicated problem, and we'll end up using this test to determine what we've got, and we'll talk in a little more detail about the way that one attacks these sorts of problems. An aquarium is to be built out of glass. It will have a rectangular base and rectangular sides. There will be no top. The length of the base will be twice its width. The volume is to be 36 cubic feet. Our job is to find the dimensions of the aquarium that minimize the amount of glass needed to build it. Now, in problems like this, the first thing you should do is draw a picture. And the picture here is pretty easy. We've got a rectangular solid here. That's the base. There are the heights, and there's not going to be a top. The next thing to do is to choose appropriate variables to label the diagram. Now, in this particular problem, you'll notice that the length of the base is supposed to be twice its width. So what we do is the width we label with x, and that means the length of the base is going to be 2x. We'll need another variable for the height, which we'll take to be y. The next step is to use the diagram to obtain equations for the objective function and the constraint. Okay, the objective function is the thing we're trying to either maximize or minimize, and here we're trying to minimize the amount of glass used, so we need an equation for the amount of glass, and that comes from the base is x times 2x, so the glass that we're using for the base is 2x squared. This front face has length 2x, height y, so the area of that rectangle is 2xy. There's a back face as well, and that's why we have two of them. The side is x times y. We've got two of those, and that gives us our 2xy. Do some algebra. We've got 2x squared plus 6xy. Now the constraint is the volume has to be 36 cubic feet. So V equals 2x squared times y, and that's 2x times x times y, and that's got to be 36. Okay, next step is to use the constraint to solve for one of the variables, and we get that y is 36 over 2x squared, or 18 over x squared. We do this so that we can plug into the objective function to get a function of one variable, which we do 2x squared times 6x times 18 over x squared, which we simplify to 2x squared plus 108 over x. Now the next thing to do is to find the domain of this objective function. These are the values of x that make any sense in the problem. And pretty clearly, x can't be negative, but it also can't be 0, because then we would have an aquarium of volume 0, which is not 36. But pretty much any positive x will allow us to make an aquarium with the right volume by making this choice for y. So that our domain is actually 0, infinity. Now the next thing to do is to find the critical points in the domain of the function. And we do this by taking the derivative of the objective function, which gives us 4x minus 108 over x squared. And that's because the derivative of 1 over x, which is x to the minus 1, is minus x to the minus 2. Okay, we're going to set that equal to 0. We do some algebra and get 4x cubed is 108, which turns into x cubed equals 27, which is x equals 3. Next, what we want to do is check possible values and see which of them, if any, is the global minimum. And here, 3 is the only possible choice, as there are no endpoints. However, it's a unique critical point. So if it's a local minimum, it is the global minimum, and we can test that using either the first or second derivative test. Here we're going to use the second derivative test. We calculate g double prime, which is 4 plus 216 over x cubed, and the reason is that the derivative of x to the minus 2 is minus 2x to the minus 3, which is how we get to here. And the question is that positive or negative? It is in fact positive for x equals 3, and that means we're concave up, which means we've got a local minimum, which means it's the global minimum. The next step is just to find what the dimensions are, and we know x is 3, which means that the long side of the base is 2x or 6, and the height is y equals 18 over x squared, which is 18 over 9 or 2. And that gives us a 6 by 3 by 2 aquarium.